All right, good morning. Uh, I'm Bill Geyer back again, and this work is basically based off a lot of the work that I've done with Heli Auto-Tune. The idea behind Heli Auto-Tune was to get a frequency response and be able to predict kind of how far you can take the gains before you hit instability, and then kind of step into that tune in flight. And so this takes it kind of one step further, but basically you can do it at your desk, so that you can basically find the frequency response of the bare airframe, come back to your desk, or do the flight, come back to your desk, and then be able to tune the aircraft at your desk, and then go out and fly the tuned gains, and then verify that what you've tuned is good. I've done this with a few different helicopters, one with a tandem, and then on some of my own. So what I'm going to do is I'm going to step through my brief. First, I'm going to kind of, for those that are not as familiar with time to frequency domain, I'm going to kind of talk about the difference. Then I'll go into kind of what is a good tune in a frequency domain. What are you looking for when you're looking at this frequency response to say that, hey, I'm getting a better tune. And then I'll go into a little bit of theory behind the predictive capability of this tool and then I'll go into what the tool features are, and then give a little demo. So moving from time domain to frequency domain, so the multi-rotor auto-tune kind of works in the time domain. It kind of does a twitch. It's looking for kind of the overshoot and the undershoot, and it's then kind of basically it's kind of looking at the free response, what we would call the free response of the system, to basically be able to then determine kind of what's the oscillatory nature of that free response, and then be able to then tune the gains on that. And so this takes it a step further, going into the frequency domain, and things that we're looking for to characterize the response in the frequency domain is what we call gain, which is basically the ratio of the output to the input in amplitude, and then also phase. And so we can see here our input is the blue, our output is the red, and we can see that the gain would be then just the magnitude of the output divided by the magnitude of the input. And we can put that in, a lot of times you'll see it in decibels, which is just a scaling for that. And then the phase is basically looking at, what's the phase between the peaks of the input and the output. And so here we're showing that here's the input, and typically your phase is going to be negative because the peak of the output is happening after the peak of the input. And so basically what we do is we look at this time between the peaks of the input and output, and then we can kind of quickly be able to determine, based on the period of the frequency, then be able to determine what that phase is. Again, like I said, most of the time you're going to be looking at negative phases. And if you see in your response that you're seeing positive phases, then there's something wrong. There's some problem with the data. So just be aware of that. So again, now kind of go into the idea of looking at the frequency response. What I've plotted here is basically a second order system, a simple system where basically we have see kind of well damped here, where it just comes down with a peak, and then kind of a more lightly damped mode where you have this peak here. And so again, that's kind of what we're looking for in the frequency response, to kind of tell whether we've got some areas where at that frequency, if you were to excite the system, you're going to see this overshoot. It's not going to stay with the input request. It's going to actually overshoot that input request. And so that's what this is indicative of when you look at your frequency responses. And real quick, for gain plot, when we show decibels, 1 to 1 is kind of what you want, and that's the 0 dB line. That's kind of what you want you want that to go out as far as you can before it drops off. You don't really want to go much above, because that means if you have it going above, then you're seeing some sort of overshoot in the response at that frequency. All right. So what defines a good tune? You want your attitudes to closely match the desired attitude. And we kind of look at that, you'll look at that in the time domain. You'll go into your log and you'll be like watching it your log to see how well does, that your actual attitude match the desired attitude, or your actual rate matches your desired rate. And that's kind of indicative of what that good tune is. And so the same idea here is you're looking for that on the gain plot, you're looking for that line to kind of go along the one, or go along 0 dB, which is basically a 1-to-1, meaning that your output is equal to your inputs request. And you really don't want to have any type of increase in that gain as you go out to higher frequencies. And so basically, I kind of drew this in there. It's a little shaky, but basically you want a good tune is really indicated by your gain plot going out as far as possible along the 0 dB line. And then at some point it is going to drop off, and that's okay, but you're looking to see that drop off as far out in frequency as you can within the capabilities of the aircraft, right? And the aircraft's going to dictate that. And then your phase, you generally want your phase to drop off as well, but you want to see that it doesn't drop off too quickly. Filters and other things that's like that are going to cause that could cause a lot of phase delay or cause this to drop off quicker. So you're really try to minimize how quickly that phase drops off out at the higher frequencies. So that's the basic idea behind, in the frequency domain, what do you want to see? How do you want that to look in order to dictate a good tune? So a little bit about the theory behind this. Like I said, I've really been working to try to look at, hey, are there better ways that we can, figure out how well we can tune a vehicle and optimize that tune, or at least be able to do that in an easier fashion rather than going out and doing multiple frequency sweeps or multiple twitches and continuously doing that, taking 5, 10 minutes of flight time to really tune the aircraft, when you can just basically go and do one sweep, come back, kind of fiddle with it at your desktop, and then go back out and fly and be confident that you're going to have a good tune. So basically this it goes along this theory where we're assuming that the aircraft is a linear system. What does that mean? Well, it basically means that we don't have any discontinuities or nonlinear kind of effects where we have either rate or acceleration limits. Those will affect our linearity. We're assuming that the tune, like our gains, aren't changing over time. So if you're using something like what is that, the SR, the slew rate limiter type thing, that would be bad, because if it comes into play, then that's going to change the gains over time. So you really want to make sure that your system is basically staying consistent with the gains as you're doing this frequency sweep and as you're looking at this tune. So what this does is then it goes, the first part of the analysis is determining the bare airframe response, right? What does that mean? Well, that's basically, the bare airframe response is basically, you take the input to the motors class and you look at the output response from the aircraft, and you figure out what that transfer function is, or what that frequency response is. And that's what we call your open loop transfer function, right? That's the open loop frequency response of just the basic airframe without any control wrapped around it. Oops. And then what we do in the math is we wrap the loops. We basically apply all the control laws analytically, right? We basically wrap these loops analytically, and it's done through, Laplace transform. Really, we're doing Fourier transform type math that we're looking at this in. I'm showing it Laplace transform, kind of Laplace domain here. But basically, the closed loop response is basically looking for the response of the aircraft, this response divided by the, with respect to the input from the pilot or whatever's making the inputs to the system. And so that's our closed loop response. This math here basically is the math that basically goes and does that, working on the frequency response data that's in a complex form, complex number form. So here's the control law diagram. Basically, I had to go through the code and figure out, thanks to Amilcar, I think he wrote kind of did the control law diagram there and helped out with that. I think you had as well, Leonard. But basically using the control law diagram, making sure I understand kind of where all the filters are and where they're making inputs in, what data they're pulling in. And so this is basically a representation as a wired diagram of the control laws for the attitude controller. And you can see here's the aircraft, the open loop response of the bare airframe. And then this is the measured rate, which Leonard gives that to us through the sysID mode as the unchanged GY, GX, and GZ, which is the gyro rates. And then we can apply the filters in the INS gyro, the notch filters, and then feed this back into the different rate and attitude controller. And then we're applying the low pass filter here, applying the error notch filter here. Here's our PID transfer function. So that's all the rate. That's the rate PIDs that's contained in here. We have the target filter for the low pass, target notch filter. And then we have our attitude feedback where we compare it to the desired attitude or the target, and that gives the correction rate to the rate controller. And up here we have the feed forward path for the rate controller as well. So this is the basic control law diagram for our attitude controller, and basically this, or actually equations then now are the equations that define that I use to calculate the transfer function or the frequency response for the rate controller, and then for the attitude controller down here. Questions? Okay. All right. So how to use it? You're going to go out and you're going to do a frequency response, or you're going to go out and do a system ID mode flight. And you'll most likely want to use because we have a lot of shaping with the sysID axes 1, 2, and 3. Those are like the pilot input axes. There's a lot of shaping there that could affect, like you have these rate limits and acceleration limits. Those could affect the results. So you probably don't want to use those. If you have to, that's fine. You probably won't be able to compare some of the calculated to the predicted, because if those limiters kind of come in, that would affect the results of the calculated. But in any case, you want to use SID axes 4, 5, or 6, which is for the roll, pitch, and yaw, which we call recovery roll, which basically doesn't have the feed forward enabled. And then you'll have that data. One note here is that make sure you do all your filtering ahead of time, because the filters will affect the response. So make sure you go ahead of time and get your filtering in there for the INS gyro and the notch filters in there on the gyro signals. So get those filters completed, and so your control signals show very low noise. In most cases, the SID or system ID logging rate of 100 Hertz is fine. It's mostly what I've used in all of my stuff, maybe for Andy where he's running the fast rate loop. Probably 400 Hertz is probably going to be more applicable. But remember, the logging rate is set for the system ID. The logging rate is set for using the log bit mask, fast attitude, medium attitude selections there, and the combinations of that give you different rates. Lastly, the SID magnitude, you don't need large magnitudes for the oscillation. Less than 5 degrees is plenty. I typically use 5 degrees. Sometimes I'll back it off to 3 degrees if my tune isn't as good and I'm seeing a lot of the aircraft overshooting a lot. You can back that off. Again, as I note there, if you see the oscillation starting to grow more than 10 to 15 degrees, stop the system ID, retune, try to get a little bit better tune to keep the aircraft from getting too large of response. The concern there is that, it continues and all of a sudden now the aircraft goes unstable and you crash. So, if you see things starting to grow and it gets scary, stop the system ID, come back out of it, try to retune a little bit better and go on from there. Again, big warning, you want to have a stable initial tune. And the big thing that's going to probably creep up and could hurt you is basically those low frequency modes. So what we consider the long term or the phugoid mode type is basically what's going to be probably your biggest nemesis in trying to do this. So trying to make sure that's stable so you don't get any type of large oscillations is going to be good. All right, so tune the tool. So it is published and out there online. And so the first thing you do is just basically start by loading a log file from your system ID flight, and you choose your file. As far as the FFT window, 1024 is a good for 100 hertz. You could go a little higher if you're looking at 400 hertz data, but I found 1024 works well for 100 hertz data. Next, once you've loaded the data in, you can then choose your axis that your sys-ID mode was conducted in, and then you can select the time, the start time and the end time. So one thing about this is that thanks to Andy Piper for a little bit of help that he gave me, thanks to Pete Hall for all his help in this web tool. But Andy was able to set it so the web tool only looked at the start and end time of the system ID run. Well, in this case, you can see that I had 3 system ID runs, and so it took the start and end time of all 3 of those, which in between I went, turned off system ID and did it another time. The tool right now will only work for a continuous system ID, right? If you have an area where you weren't in system ID and you were maybe in stabilize or another mode, then it's going to cause problems with the tool. And the reason being is that some of the parameters or some of the signals it's looking at when they're not in system ID mode are sampled at a different rate. And so all your signals need to be sampled at the same rate, and that's why we only look at data that's in the system ID mode. And so now I've selected one of my system ID runs, and so I've got that set. And at this point now, I hit the calculate button down here at the bottom left-hand corner, and that will do the initial calculation of all the frequency responses based off of the actual data. Here's the INS settings. These will be loaded in automatically when you load your log file. The INS settings for that system ID run. So they have the 2-notch filters. They have the INS gyro sample rate and filter, low pass filter there. And then we have the loop rate is up here for the loop rate, and then we have the attitude control parameters for that axis that you're trying to tune. Over here on the right is the notch filter, the PID notch filters. Right now we don't have any selected, but if you select one of them, and you can add those in, right? Maybe you didn't have PID notch filters, but you can add that in with the parameter settings, and then quickly add that in and be able to look at how that affects the tune. So what I show here in each of the plots, so this is the plots you'll see, and it shows basically the gain plot in the top, or amplitude in decibels. It shows the phase plot in degrees. It doesn't wrap well, so you'll see it goes from -180 to +180. That's one of the future improvements we want to do, is try to get that wrapping to work. And then down at the bottom is most important is the coherence. Coherence speaks to the goodness of how well the output correlated to the input, right? Anything below 0.6 is generally not trustable. Above 0.6 is good. More closer to 1 is even better. But so, in this case here, you probably can go from maybe 2 or 0.2 hertz to maybe 8 or 8.5 hertz. So, that's the important thing here is I show all the data. You want to basically make sure that what you're looking at and what you're using to tune has good coherence. And so for the predicted value, I use the bare airframe coherence. So you have a reference of what the bare airframe coherence is, because that's what the prediction is based on. And so that's put in there so you kind of have a reference as what your prediction was based on. So there's different selections at the bottom, and I'll go to the tool here in a minute. So here's the bare airframe response. I believe this is a multi-rotor. So you see that here, yeah, 90 degrees phase. You can see there's a little bit of wrapping here, but acceleration command system for bare airframe of a multi-rotor. And again, this is what the algorithm's using to predict the closed loop responses. And here's the parameters that it's using to generate these transfer functions or these frequency responses. So again, remember that all the calculated lines here are based off of actual data. It's going into your system ID flight and grabbing the data at the different points in the control laws to give a comparative frequency response that would be equivalent to the frequency response that predicting for the rate loop, for the attitude control loop. So for the rate controller, here's what the parameters we're picking for the calculated responses for X, Y, and Z, or for pitch, roll, and yaw. And then here's the comparison. Again, this compares initially what you're getting based on the parameters. So it should compare well. When you do this, you should see a good comparison between what you ran and what was predicted. If you don't, then there could be some nonlinearities in the system. Maybe you had some acceleration limits or something about your system, your aircraft has some nonlinearities to it. So just be cautious. That's a good way. This is a good way to check to make sure that you have a good prediction. Controller shown, and so here's the parameters it uses to do the calculated frequency responses for attitude controller. And again, there's the predicted stuff, and you can see it compares really well. And then finally, input shaping, right? So this is now going from what the pilot's going to make as far as an input or the autopilot, and then looking at the frequency response of what the response is to the pilot's inputs. And this includes those for the attitude controller includes the input shaping or the input TC, input time constant, right? So that's why you see this roll off here of so here's our attitude controller loop. Here's the input shaping. You can see it kind of rolls it off because that's the input shaping of the input TC causing that. All right, so let's go ahead and look at an example here. Hold on a second. Let's see here. I have it. There it is. Okay, so I loaded up. This is a tandem heli that I recently helped provide a little better tuning on. And so it's just for the pitch axis. The user was complaining about there was like a low frequency oscillation going on and needed help with the tuning. So I had them do a frequency sweep and I took the data, loaded it, hit calculate, and then it loads all the parameters. And then I get my initial frequency responses for the rate controller compared to the calculated ones. And so we can see in the response here, you can see a little bit of a rise. You can see it's like almost a 5 dB rise, which means it's like almost a 2 times, the overshoot was almost twice of what the requested input was in the rate response. And then we kind of see back down here, it goes back to 1 or 0 dB, but then we see a little bit of a rise out at maybe 7 or 8 hertz, which is essentially one of the modes of the aircraft, kind of a lightly damped mode of the aircraft that we want to try to control better. And so initially what I had to do was and kind of what I'm looking at now is just the gain plot. I said, well, I want to get rid of this low frequency oscillation. So because it's a tandem rotor helicopter and it's a pitch axis, it acts more like it behaves more like a multi-rotor, right? Because you have these two rotors that are commanding differential thrust. And so basically I said, well, that's probably because it's more of a feed forward thing. So if we bring down the feed forward, right? To reduce that. And at some point you saw that the feed forward, it doesn't change the response anymore. Kind of went down. So I got down to about point, oops, I went the wrong way. There we go. So reduce this down, and we can see that now it's starting to flatten out around 1. I can keep it there, and now I can start bringing up my D gain if I want to bring up the D gain to see how much I can bring that up. It's at 0.006 now. And so it automatically starts calculating immediately. And you can see the peak isn't getting any larger, but I have to be careful out here because I'm really close to where my data has poor coherence. So I kind of have to be careful about how far I push this out, or maybe go get additional data. But let's go ahead and bring up the P gain. That'll help hopefully flatten things out. So as I bring up the P gain, you can see this is all kind of now flattening out along the 0 dB, except for when I get out here, I start seeing now again the this almost 10 dB. No, I'm sorry, like a 6 dB rise. So it's like 3 or 4 times overshoot. So at this point, now I can start, I can introduce what I found with helicopters is that you could reduce these lightly damped modes out at these high frequencies by basically just adding a notch on the target. And so if I add a notch on the target, I can now put that notch in here. I just have to put in the parameters. There's the same parameters that you're seeing when you put them into the actual mission planner. So filter type 1, now my notch frequency, I look down here, see it's around 7-ish hertz. So I can put 7 in there. And so there you go. You see it kind of immediately put this, you can see the notch taking effect. 40 dB for helicopters. That's why I went back and talked about yesterday that, really what I'm just trying to do is shape, kind of take the rise off of there, kind of shape it so it just flattens it. And so I don't need 40 dB. I can get away with maybe, let's look at 8. Still a little bit too much. How about 5? Yeah, so I'm starting to flatten it out a little bit. I can take and maybe widen the notch. It'll make me 1.5. And that kind of widens things out. And kind of now, at least now I don't have that peak there, which means I don't no longer have that overshooting that's going to happen at that frequency. If I get hit by a gust, or if I'm making inputs, I'm not going to see the aircraft responding by overshooting a lot. So again, I can now take that and look at, and so here's the different selections down at the bottom for the control loop. So I can look at the attitude controller at that point and see what I got. You can see I get a nice flat line going along 0 dB or 1 to 1 as it rolls off. And then I can even look at the imp shaping that I might have on this. And then that shows kind of what the pilot's going to see from their perspective when they make inputs to the system. I think that's all I think that's all I got. Questions?
So a question about your workflow then, typically, in terms of, because you've got a predicted step, what do you do in terms of your like pre-post? How do you then, once you go flight test again, what kind of things are you looking for to try and see that what you've done predicted previously now is matching reality once you've applied the changes and tested?
Yeah, so if you go out and run the frequency sweep again, when you come in and load it, your gains will all load up as what you had in the aircraft. And so you're looking that, that the predicted matches the calculated. And that's kind of your verification that, hey, the changes I made are actually good, and everything matches well. I mean, so they should match exactly, very close to what you I mean, yeah, I mean, it should match. Yeah, it should match very close.
Very interesting. How happy are you with the abstraction and transplantation of the actual controller versus the replica you have here that predicts the new response?
Yeah, I mean, I'm very satisfied that, so with that, as with everything, take it with a grain of salt. You're going to go, I would not suggest that you just immediately go out to the new gains. I mean, you got to be careful if you don't understand entirely what's happening here, right? This is more designed for folks that have some understanding of frequency response, flight, and frequency response testing and kind of playing and doing this type of analysis. You can't just go and say, well, I'm going to just drive up the D gain and maybe the peak is actually off of your chart. You have to be I would take incremental steps, look at something, make some inputs or make some changes, then go out, fly it, do a frequency response, get the SysID, get more data, kind of make sure it matches, and then just kind of step yourself into your new tune.
Yeah, your mileage may vary, of course. My question is more like from the standpoint of someone who has tried to make mathematical representations of the actual code we have in the code base. How easy did you find to do this abstraction from the code base to the tool you have here?
Yeah, I mean, so it wasn't, bear in mind, you have to kind of, I've been working with Leonard for a number of years now, so I understand the code base fairly well. There are the nonlinearities are what you have to be worried about. I mean, yeah, you kind of have to know where the rate limiters and the acceleration limiters kind of rear their ugly heads. And so that you can, and basically, like I said, that is not included in this representation. That's outside. It's really difficult to do as far as predicting that kind of stuff. Again, we're looking at a linear system, so you got to keep your amplitude small and the rate small, so that basically you stay within that linear response.
Excellent. Thanks.
Just on that point, within the code, would it be possible if we were to start logging just some flag of some description when we start tripping over some of those limits? Oh, I've just been told by Leonard we do. Okay, so maybe we could, as a next step, we could just start putting some warning flags in this tool,
Yeah.
just so it takes a little bit of the guesswork out of are we tripping into that non-linear?
Yeah, no, and that would help, verify that if you're seeing some differences between the predicted and calculated as to, oh, well, yeah, potentially I've got some, I see in the log that I hit some rate limiters or acceleration limits. So yeah, then you kind of know.
I sent a cryptic message to you on Skype too, and we may be able to do things like look at our rate limits and adjust the magnitude throughout that sweep as we get to the higher frequencies to keep us from hitting the rate limits. Because it's quite deterministic. There's a question on Zoom. Can you get stability margins from this tool? Do you have plans to add this if not?
Yes, there is the possibility to rework the frequency response, or to rework the transfer function to do what we call the broken loop, kind of a broken loop transfer function that would then be able to then identify what your stability margins would be. I think I took a stab at it, and I hadn't fully worked it out yet. The other thing you could do is you could go and provide transfer function that would predict the disturbance rejection bandwidth or the disturbance rejection frequency response. And so you could then go in there and kind of look at how your disturbance rejection compares to what you'd and tune that.
One of the reasons why I prefer having the graph wrapped the way you've got it up here is you can clearly see where it crosses the 180 degree point. And
well, and there's a selection down here. I kind of left it in there, but the unwrap, you can select between wrap and unwrap. You can select between linear, as far as the scaling of the gain between linear and dB. And Pete Hall had done all this work up front, so he made it super easy for me to basically be able to glom onto what he did and be able to to make use of this graph and really have a powerful tool. Any other questions? In the back.
I mean, I would just say thanks very much for adding an excellent web tool, and I really hope this is sort of the future of tuning ArduPalette. And
Yeah.
hopefully we can, or I'd like to in the future, you know, we'll add tool tips and make it a little bit more user friendly like some of the other tools, and try and get some documentation and things. Because I know this, or if you're not familiar with this stuff, this is quite overwhelming the sort of first time, and certainly
Yeah.
it's
And that's
taken me
why
a
I
long
caution
time.
people to, you know, be careful in using it, you know, take baby steps when you're looking at tuning things. Yeah. So and I ultimately, you know, Leonard and I have talked about this. Hoping somebody comes along, or maybe if I feel that that I can really do that, is to actually have a separate thread that would run in AutoTune that basically would do this, you know, what I'm looking at and doing graphically, that it does it in AutoTune, and then basically you do one sweep at AutoTune, runs a thread, does the calculations, and then comes back with a new set of gains. You do a second sweep, it verifies that you're done. But again, that's a lot of work to take what you look and hear and then, you know, figure out how you're going to change gains. It's a
Thank you very much. Brief clarification. Apologies if my understanding is a bit layman on this, but you mentioned the criticality of having your INS and your notch filters established prior to going into this tool. But then you showed early on a couple dialog boxes where you were kind of evaluating those. So does this give you the capability to evaluate the quality of your filtering as well, or is it really absolutely critical that that's perfect going in?
It's not. So the big thing about filtering is just making sure that you don't have that your noise levels in your control signals are not such that it's limiting your tune capability. It's going to show you. It will show filter, you know, a possible gains of filtering, you know, that a better filtering, or maybe you've filtered too much and it's going to show that you've you know, you've got a lot more phase loss because you have too much filtering at the INS level, right? So yeah, that would, you certainly could use it to kind of evaluate your filtering, but only in the control band. You know, notice that I don't have I'm not getting good frequency response out at where like my notch filters for helis are at like 20 hertz, right? For the rotor modes. So I'm not out at that point. I'm only looking at the control, kind of the control frequencies. So again, yeah, I don't have good, well, I didn't do the frequency response out that high, but yeah, I don't know that you'd get good, good coherence all the way out to those high frequencies. So certainly you could tell how it affects your control range of frequencies. But yeah, probably the filter tool would give you a better awareness of how you're doing on filtering out noise.
Wonderful. Thank you very much.
Yeah. Oh.
Yeah, it's sort of important to understand the limitations of what we're dealing with here. This tool is good for evaluating your controller performance and how to get the optimal control. That doesn't mean that by setting your these PID values at your optimal control values that you won't blow your ESCs up with the level of noise you pass through them with those filters. And there's always this trade-off between the amount of filtering you're using to keep your noise levels down. And that's why if you've heard some of my previous talk, I talk about hardware limited tunes, where if you tune it too tight, you know, ESC's blown up. Talk about noise limited tunes where, you know, your ability to tune an aircraft up to its optimal is actually hampered by the fact at that point 50% of your output's noise, and so you're actually backing off your tune to limit your noise or adding a lot more filtering than you ideally would like. to bring that noise down. And so you do have to, like, you know, this is a tool that helps you work out what that optimal tune looks like, but then it would, you know, in conjunction with the filter tool, you then may be able to apply those gains to the filter tool to get a bit of an idea of how much noise is passing through and whether you are reaching unhealthy levels of noise. And the other key limitation of this tool too is it is only looking at that single state, that hover state. We then, as we're flying dynamically, we start pushing into various corners of our flight envelope, which push the system gains. We don't care too much if it pushes the system gains down a little bit, but those corners, those dynamic corners that push the system gains up, and can then cause oscillation there. So your optimal tune at hover, when you start considering the entire flight envelope, may need a little more gain and phase margin than perhaps you would otherwise like to have if you're only hovering.
Yeah.
So
that's a great point, because again, it's assuming a time invariant system, right? Meaning that your gains are not changing over time. The system isn't changing over time, meaning the aircraft bare airframe. And yes, no doubt that when you go into forward flight, your bare airframe system changes. And so, you know, you're gonna have some changes there. So what Leonard's saying is definitely very accurate as to, you know, be careful, you know, if we have the ability in the future to do system ID or run the system ID. I think you can run the system ID mode in with a little bit of forward push on the stick to keep it at a speed, and then be able to then evaluate the same thing at forward flight.
yeah, and then we get our dynamic maneuvers like braking that can spike your gains, your system gains considerably. And then on top of that, you need sensible limits to ensure that while you're actually running, when you're actually hitting those saturation regions, you are coming into those saturation regions and coming out again in a controlled way. So this is really that core thing to help with that fundamental tune. And from my perspective, thank you, thank Pete, thank everybody, because this has been one of those little things that's been stepping on little changes, little drops of engineering, you know, little pebbles of engineering. I'm just glad that they're pebbles and not breadcrumbs, if you know what I mean. So thank you very much.
I think the power of this tool is not only the fact that you can kind of sit down at your desk and do it, but it really, like, we have so many knobs that we can turn in this control structure. And just being able to see, like, the whole thing of like the feed forward affecting that low frequency response, like, oh wow. And I started reducing the feed forward gain. I was like, oh yeah, here it comes down. And now once I get it below a certain level, I can actually pump up the angle P gain and not affect that feed forward, you know, that low frequency. So yeah, like I said, the insight it provides is just, yeah, it's really great. It just really, that's why I really like this, because it provides so much insight as to what all these knobs do and how they change your tune. And I guess one more point is, and it goes back to the question that was in the back, is I think a lot of what I'm seeing here, as far as the limits, like I don't know if this user did this out to 10 hertz. I can't remember but I think what you'd see if there was a lot of more noise in the system is you'd probably see your coherence drop off earlier than what your frequency sweep went to. Like if I did my frequency sweep out to 15 hertz and I saw my analysis was only good to like 10, there's probably some noise in there that's probably causing it to not have a good coherence at those frequencies.
System ID is set up with numerous different inputs too, different input points. And so if you want to examine the high frequency response of your system, it's much more dangerous, but we do have the ability to pump those signals directly into your actuators. However, the scope for things to go bad there dramatically increases. The slowest inputs is up at the angle. So if you really want to push your upper bandwidth sections to look at ESC and frame resonances and things like that, which we haven't really played around with this tool yet, that's where the actuator inputs will potentially be very interesting. But they'll be less interesting for tuning potentially.
Any other questions? Oh.
複数 IMU があった場合、それぞれについての IMU についてチェックすべきなのか、それとも、メインの IMU だけをチェックすればいいのか、どうでしょうか。
Right, so the question is, if you have more than one IMU, do you need to? All right, sorry, so the question from Murata-san was, in the case of flight control with multiple IMUs, do you need to perform the system ID check more than once, or is just once good enough?
So once, but I guess, how does that, it's more than one IMU? Don't we use the primary IMU? I don't know that I can.
We should only be able to perform that once, unless you start getting into the realm where Andy is working, where you're pushing so fast that your IMU update rate, you're getting different IMU update rates and that sort of stuff. In our normal setup, for most aircraft that are running at a much lower update rate, all of the IMUs will behave the same. Yep.
Thanks, Leonard. All right, well, thank you.